So the quants reading has basically 3 chapters. First chapter being multiple regression, second chapter being machine learning, and third one being big data projects. Let me start. So you have to know the 5 assumptions of multiple regressions. Basically linearity. The relationship between the independent and dependent variables are linear. Then homoskedasticity. The variance of the error are same for all and are constant. If it is not same for all and constant, it becomes heteroskedasticity. This is an issue. Then third one being the independence of the error term. The observations are independent of the error of each other, meaning the errors do not correlate at all. The residuals are not correlated at all. If there's correlation, then we go for serial correlation. Then comes in normality. Errors are normally distributed. So the error in the error terms also there's normal distribution being there. And then the last one being independence of the independent variable, meaning the independent variables over here are independent of each other, meaning that independent variables are not random. And if they are not independent, then there exists multicollinearity, meaning that the independence variable explain each other's independent variable. In that there are subparts of A and B. The subpart being independent variable are not random, meaning that they are somehow correlated and they explain the dependent unit. And second one, there is no exact relationship, linear relationship between 2 or more variables. And the expected value of the error term, what we expect the error to be, is 0. You have to understand this thing. Then comes the R square, meaning how much can the independent variable explain the dependent variable. Total squared sum minus error squared term divided by TSS, meaning explained variable divided by total. That is R square. And if we go for adjusted R square, it will be 1 minus n minus 1 divided by n minus k minus 1 multiplied by 1 minus R square. Adjusted R square basically penalizes overfitting. You have to keep that in mind. And for AIC and BIC, AIC helps in forecast and BIC helps in fit. And lower any of these terms, the better it is. Then we come to the joint hypothesis test. So there are F test and T test. F test becomes for the whole regression model and T test is for the individual independent variables. So F test over here, where we have degrees of freedom, is equal to n minus k minus 1. So it is the squared sum error of the restricted unit minus the squared sum error of the unrestricted unit divided by the restriction. The whole thing divided by sum of squared errors of the unrestricted unit divided that by n minus k minus 1. And a special case for this would be where F test, where all other observations are 0. So sum of squared residual of unrestricted divided by k, the number of independent variables, divided by sum of squared error of unrestricted divided by n minus k minus 1. So these are the 2 tests in hypothesis testing where you have unrestricted and restricted to find out whether if independent variable is significant or not. The test being over here is that the null hypothesis being B2 is equal to B3 is equal to 0, meaning that B2 and B3 both are insignificant. And if this value, the t-test ft test value, is greater than the critical value of the f, then we can reject the null. Rejecting the null meaning that h0 is not equal to 0. Meaning that the second independent variable and third independent variable are significant, meaning they have explanatory power. Then F test being the overall fit of the model and T test being the individual significance. Then be vigilant about the 3 misspecified items. If there's omission of variables, if we have omitted an independent variable, we'll have biased parameters, inconsistent coefficient, serial correlation, or heteroskedasticity in the error term. And if we have done inappropriate forms, meaning that if we have not taken the log of the value or if we have not converted any values to their appropriate metrics, then we'll have heteroskedasticity in the error terms. Inappropriate scaling, heteroskedasticity and multicollinearity, and inappropriate pooling of data, heteroskedasticity and serial correlation. The common are 3 violations which happen. So basically heteroskedasticity, meaning that the variance of the error term are not same for all. Variance of the error term are not same for all, meaning it is conditional. So that is one of the violations. And to correct that violation, we go for a test called as BP test. BP test meaning Breusch-Pagan test, which is for conditional heteroskedasticity. We are alright with unconditional heteroskedasticity, but we are not alright with conditional heteroskedasticity. So for that, the test is H0, meaning the conditional heteroskedasticity exists. So it is a one-tailed test. H0, if it is greater than the critical value, then we have to reject the null. The BP test says that n into R square of the restricted unit with degrees of freedom of k is the BP test. You have to keep this thing in mind. Then serial correlation means that the residual are correlated with each other. So to correct this, we use DW test, Durbin-Watson test. So in Durbin-Watson test, we take the help of autocorrelation, so AR1, AR2, and we take BG test. So for serial correlation, we take the help of DW test and BG test. So DW test is only for the first lag, the autocorrelation of 1, AR1, and BG test can be for multiple lags. In that BG test, the null hypothesis says that P1, the lag of the residual, is equal to 0, meaning that there is no serial correlation. If the test stat is greater than the critical value, meaning that we can reject the null so that no serial correlation exists. N minus P minus K minus 1 is the degree of freedom. Then we come to the third one, being multicollinearity. So in multicollinearity, it means that two or more independent variables are highly correlated with each other. To correct and test that, we have VIF test. So in VIF test, the test says that 1 divided by 1 minus R square of the J term, stating that if 1 is the number of if VIF is equal to 1, then R square is equal to 0. So no high correlation. If VIF is higher than I, we need to investigate, and it is higher than 10, then multicollinearity exists. So these are the three violations. You need to understand that. A simple mnemonic which you could recall is that just think of that you have a BP condition, and a serial killer always needs to have a bag to carry his weapons, and if you need to talk to multiple people, then you need VIX. In this way, you could remember it so that you don't need to have any. Now coming to the next one, outliers. So outliers are basically extreme dependent term, and high leverage point being extreme independent term. Then you don't have much in that. It's just saying that if the high leverage point is between 1 and 0, then we use t-test being error divided by the square error. Then we come to the ordinary regression. Then an important point being ordinary regression is not suitable for quantitative stuff like probability. So for probability, we use log odds. In log odds, it is log fors and log against. Log for being probability divided by 1 by probability, and log against being 1 minus the log for. And then log odds is basically you add an logarithm term before the odd, and the assumption is that it is normally distributed but it has fat tail, and the coefficient is estimated using the maximum likelihood. This maximum likelihood comes from here. So its maximum likelihood ratio is equal to negative of log likelihood of the restricted term minus the log likelihood of the unrestricted term, and this usually is a negative value which is closer to 0. You have to keep these three things in mind. Now coming to nonlinear and trend models, starting with the basic linear regression, which is the dependent variable is equal to B0 in the intercept plus B1 coefficient of the t, which is an independent variable, plus the error term. Now this is good for relationship between dependent and independent terms if they have a linear relationship, but it is not good when it has a non-linear relation like trends. So in trends, we just take the log of the dependent value and assuming constant growth over here. Here we are not assuming any growth. This linear distribution is good in non-linear relationship between two variables. The residuals or the errors are basically serially correlated. So for serially correlated errors, we take log linear value. There are some limitations of the trend model. So log linear value is the trend model. The limitations are residuals are uncorrelated, and a time series without serial correlation is equal to Durbin-Watson test should be approximately 2. And if it differs, then serial correlation exists. You have to understand this point. Recall that the mnemonic we said that the serial killer has to have a bag. You need to have bag, BG. Breusch Pagan test. So remember the mnemonic which we said, if the serial killer is there, you need BG test and DW test, as we showed in the other slide. AR model, auto regressive model, meaning that the previous lag can explain the current term. So we use past to predict the current value. So for AR model to be stated rightly, we need to check that if the AR model is covariance stationary, meaning that when residuals are uncorrelated. So residual of lags are uncorrelated. In that we have three assumptions: constant and finite explained variable, meaning that mean reverting level is constant and finite. Constant and finite variable, meaning that volatility around mean does not change much. And third point is that constant and finite covariance, meaning that there is constant residuals between the lags. You have to keep this thing in mind. Then we come to the chain rule of forecasting, which you have to remember that the first variable can A can explain B, and B can explain C, and C can explain D, and how you would get each terms from defining the previous word terms. Then test for no serial correlation. We have the test for AR1, which is T test, which is equal to 1 divided by the root T. And T over here is basically the correlation of error term 1 and the error term 2 divided by 1 divided by root T. And we have degrees of freedom of T minus 2. We have to understand this test. And if the errors are correlated, then the standard errors are unreliable and the t-test is inconsistent, meaning that individual tests are inconsistent and DW test is not appropriate. Then coming to the mean reverting level. To check if the AR model has constant and finite explained variable, we use mean reverting level to check it out. So mean reverting level is equal to B0 divided by 1 minus B1, the intercept divided by 1 minus the coefficient of the factor 1. So this gives us the mean reverting level. And to check if the explained variable is significant or not, we take the null hypothesis of checking that if the correlation exists. This symbol is for the correlation. If the correlation exists, and if it does, if the test stat is greater than the critical value, then we reject the null, saying that the correlation exists. And if so, this says that no correlation happens. At 0 says that no correlation happens. If we reject this, meaning that the correlation exists. Then comes the root mean squared error. Root mean squared error says the accuracy of the AR model forecast out of sample values. Low root mean squared error means that it has low forecasting error, meaning that it is a better model. Then now we come to the financial data. So basically financial data are not covariance stationary. So over here we get two problems: random walk and random walk with drift. Random walk means the first period is equal to the previous period plus an error term. And if the first period actually means previous term plus error term, it does not have a constant and a finite mean. It doesn't have constant and a finite mean, and it is not covariance stationary at all. It says that B1 is equal to 1. So that is your random walk. And the same thing with a drift. It means that the B0, the intercept, is not equal to 0. And if that happens, then it is random walk with drift. And to rectify random walk with drift, we use first differencing to solve it, and DW test. There's also another concept called as explosive root, meaning that absolute value of B1 is between 1. And then we come to the test for unit root, for non-stationary, DF test and AR model test, and checking for daily lags. The coefficient of variable for the first differencing. We take the first difference of the variable, then we take a hypothesis testing on it, which is equal to G. G is basically the difference between the variables, which is equal to B1 minus 1, meaning that we expect this 0. We expect this to be other than 1, because if it is 1, then G is equal to 1 and the difference is 1, meaning that it does not have any unit root. But if B1 is 1, it becomes 0, and if it is 0, then it has unit root. From here we take this. If it then edge 0, so the null hypothesis is edge 0, which is equal to G is equal to 0. And if the test stat is higher than the critical value, we reject the null and we state that there is no unit root problem. After this, we come to the covariance and non-covariance variables. You need to understand this chart. If the independent variable and the dependent variable both are covariance stationary, then we can use it. If the independent variable and the dependent variable are both non-stationary, we can use it only if they are co-integrated with each other. Co-integrated over here means that both the variables explain and are integrated with each other. And if either is covariance stationary or non-covariance stationary, we cannot use it. After this, we go to the... So now, starting with the machine learning. Machine learning, the important things which you need to know in machine learning are that the variables are continuous and categorical. So you need to understand this chart. This chart basically summarizes everything of machine learning, which is that the supervised and unsupervised learning, and continuous and categorical variables. So in continuous variables, either you can use linear regression as we did earlier. Then you have penalized regression, lassos. You have logistic regression. You have cart. Then you have random forest. A super fast snippet would be that in penalized regressions, lasso, you have a hyperparameter being lambda. The researcher need to specify that. And also in lasso, there's a as a regularization font item, which you need to be careful about. Then logistic regression is basically we just take log value of the whole regression. Then comes the cart. In cart you have a target variable, and that target variable has a nodes, so it is categorical and nodes based, so one by one it comes down and down and down. So this is how cart works. This is all supervised. And if we come to unsupervised learning, unsupervised variables would be dimension reductions. In dimension reductions we have PCA being principal component analysis. In this you have to know these three important pointers. Nth vector being that how uncorrelated are the variables. Nth value being that the total variables is explained by the nth vector. How much of the total variance is explained by the nth vector. And sweep plot is basically the percentage of variance explained by each of the independent factors. Then coming to the second type in unsupervised learning, continuous variable, would be k-means, and then hierarchical being from top to down and bottom up being that. Now coming to categorical classification. In categorical of supervised learning, you have logistic, same as logistic over here. Then you have SVM being support vector mechanism, where you get a line and you distinguish between two different categories. So you draw a line, and you also have soft margin where both the variables intersect. Then after that you have KNN, K nearest neighbors. In that you have a value, and from that value you find the nearest of the terms, of the 5 terms, and then you move to the next value, and then you find the next 5 terms, and then you move to the next one, and you find the next 5. So it's like that. And cart comes again as over here because it's categorical and continuous. Then in k-means you have to also understand you have a centroid, and a hyperparameter has to be set over here, and this is one of the biggest limitations of k-means. Then in hierarchical, the same hierarchical, you have two types. You have allogomative and divisive. Allogomative is bottom up, going from bottom, taking one item, then adding another item, then adding few more items, then going to the top, and then taking the whole parameter as such. And this is coming from top down. So from economy we are down to the country, then we are down from the country, we are down to the states, from the states we come to the districts, then we come to the individual places, like that. After that, in continuous or categorical, you have neural network. In supervised learning you have neural network, deep learning, and reinforcement learning. In neural network you have to understand there is an activation function. It's basically a node which says that yes, this can go further. It's like that. Or if that node is not, if the node is off, then this will not go further, and if it is on, it will go further. The values are passed down, and it is a forward propagation. You have to know this. Now at the last we come to the big data problems. So in big data, we start from the text problem formulation, then we go to the data curation, then text preparation and wrangling, and then text exploration, and after that model training. In data wrangling and pre-processing, we start with extraction, and then we go to the aggregation, then filtration, then selection, and then collection. You have to keep this thing in mind. Then another thing which you need to understand in text processing is that preparation stage, where the text has been cleansed, involves removing HTML tags. This is in unstructured data. So removing HTML tags, removing punctuations, removing numbers, removing white spaces. And in wrangling, basically normalizing, lower caps, stop words, and temization and lemmatization. You have to keep this thing in mind. And then comes the back of words. So for the back of words, we have no sequence over here. So you have to be careful about two things. The n-gram being, it can either be unigram, where it is just stock. Bigram, it is stock underscore market. And trigram, it would be stock underscore market underscore bad or negative. Could be anything like that. Then we would come the histograms. For understanding histograms, it's basically equal bins and respective frequencies. Density plot is basically continuous data and smoothed down histogram. Bar chart is categorical. Box plot is continuous data with mean and quartile outliers. Then we come to the unstructured data. Unstructured data, we have exploratory data analysis. In that is text classification. We have sequence of tokens, and that sequence of tokens is then termed as term frequency, where we eliminate the stop words over here. And then we also take a rare token overfitting. So when there's very rare tokens, we tend to say that the document is overfitted. So document frequency, the formula is number of words in the document divided by all number of documents. This is something which you need to keep in mind. And later on, we turn our heads towards feature engineering. So n-gram, you have n-gram as previously discussed. It is bigram, trigram, and unigrams. Then comes name entity recognition, NER. you have to be vigilant about this. So in NER, tags, it could be nouns, it could be verbs, it could be anything. It's basically a name entity recognition. How do you recognize that entity, whatever you're describing? Then comes the POS, meaning the parts of speech. Document what does the word describe corresponded to the part of speech. Over here, the normalization is basically xt, the xi term minus the x maximum divided by x maximum minus the xi term. You have to keep this thing in mind. Then standardization is xi minus mu being mean, xi minus mean divided by standard deviation. You have to keep this thing in mind. After that, we come to the error analysis. One of the important key areas to see in the big data problems is that to understand this beautifully, I have made the table, and in a way you could easily understand this. Think this as an actually what happened and what you had predicted. You predicted it's going to be a default, and actually a default occurred, true positive. And in this case, you had predicted there would be a default, and there was no default. It is false positive. And this is type 1 error. You have to keep this thing in mind. Then comes the false no default. You had predicted that there won't be any default, but there was actually a default. So it is false negative, which is a type 2 error. And in the case where you had predicted that default wouldn't occur and it had not occurred, it becomes true or negative. You have to keep this table in mind. Easily recall the whole table. I have just written a few numbering schemes which you can easily understand. So this would be 1, 2, 3, 4. 1 would be true positive, 2 would be false positive, 3 would be false negative, and 4 would be true negative. So we have precision. So for precision, it's going to be 1 divided by 1 plus 2. And for recall, it's going to be 1 divided by 1 plus 3. And basically it is true positive divided by true positive plus false positive. Recall, it's 1 divided by 1 plus 3. This is true positive divided by true positive plus false negative. These both metrics, higher is better. You have to keep that in mind. Then comes the accuracy. Accuracy starts from true positive and true negative. How accurate was the predictions? So accuracy would be 1 plus 4 divided by all of these numbers. You have to keep this thing also in mind. Then we come to the F1 analysis. F1 is going to be 2 times 2 multiplied by precision, the precision amount, multiplied by recall, the recall amount, divided by precision plus, this is plus over here, plus recall. Precision plus recall. You have to keep that thing in mind. Then second time we come to the receiver operating characteristics, which is false positive receiver and true positive receiver. False positive receiver is 2 divided by 4 plus 2. This is false positive divided by false positive plus true negative, and true positive receiver, which is going to be 1, which is true positive, divided by 1 plus 3, which is true positive plus false negative. You have to also keep this thing in mind. Then finally we come to the root mean squared error. In root mean squared error, it's basically square root of error squared divided by n, or we could also simply say a root mean squared error. That's all in the big data projects, and this is how you could easily revise the curriculum.